Very good morning, everyone. So we are looking into the solution of linear but non-homogeneous partial differential equation using Green's function method. We have developed the theory in last few classes for the Green's function solution and chalked out whatever the procedures. Let me repeat it. First, given a problem, a non-homogeneous partial differential equation in the governing equation as well as in the boundary condition, we have to find out the adjoint operator. Once we find out the adjoint operator, then you have to check whether the operator is self-adjoint or not. Next, we have to formulate the causal Green's function, and there are three rules, thumb rules for formulation of the causal Green's function. First of all, the non-homogeneous, the operator remains the same for the causal Green's function as in the original problem. The non-homogeneous term in the governing equation has to be replaced by a unit step function at a particular location in the domain, and then we have to force the boundary conditions to be homogeneous. Once boundary and initial condition to be homogeneous. So, once we do that, then we will be getting the solution of causal Green's function. After that, what basically the idea is to see the effect of the one unit step function. Non-homogeneity will be replaced by the one unit step function, forcing others to be 0, so that one can track what will be the unit impulse or unit non-homogeneous term will be giving the response in the whole system, and based on that we will be mapping on and connect it with the actual problem. So, step number 1 is construction of causal Green's function. Step number 2 is the construction of evaluation of adjoint operator. If adjoint operator is same as the operator, then the whole problem has been simplified. Then we will be from the expression of Green's function, we will be writing the expression of adjoint Green's function by changing the subscript x0 and x1, and then we will be connecting the adjoint problem with the original problem, and we will be getting the complete solution. If the operator is not self-adjoint operator, then we have to find out the self-adjoint operator, and then we will be getting the solution of adjoint Green's function, and by changing the subscript, and then we will be connecting the adjoint Green's function with the original function with the original problem, and we will be getting the complete solution. Once we do that, we demonstrated this method by solving an ordinary differential equation, and we have identified that depending upon the number of non-homogeneities in your system, whether in the governing equation or whether in the boundary conditions, there will be the solution will be containing those many number of terms. Because of the presence of non-homogeneity in the governing equation, the solution will be containing a volume integral that will be corresponding to the non-homogeneity in the governing equation. Because of the presence of non-homogeneity in the boundary conditions, the solution will be containing a surface integral over the boundaries, which will be corresponding to the non-homogeneous boundary conditions. So, if there are 3 sources of non-homogeneity, one will be getting the solution will be composed of 3 terms, 1 volume integral term and 2 surface integral term. If there are 4 sources of non-homogeneity, 1 volume integral and 3 surface integrals will be present, corresponding to 4 sources of non-homogeneity in the actual definition of the problem. So, we looked into a parabolic partial differential equation first, because the parabolic partial differential equations are quite common and they represent a unsteady state process in any chemical engineering operation. So, we are looking into the system del u del t is equal to del square u del x square plus f of x t, subject to the boundary condition at t is equal to 0. We have it was u is equal to h, boundary conditions at x is equal to 0, we had u is equal to p, at x is equal to 1, we had u is equal to q. So, we consider the initial boundary conditions on u, and there are 4 sources of non-homogeneity in our problem. So, in the last class we constructed the causal Green's function. We solved the causal Green's function using partial eigenfunction expansion method, and then we got the we have obtained the the adjoint Green's function, and with the adjoint operator was not the same operator. So, L is equal to del del t minus del square del x square. So, I am just summarizing whatever we have done in the last class in context of solution to this problem. So, what we did, we constructed causal Green's function, the method that we have adopted is partial eigenfunction expansion method. Okay. Second, we completed the solution of Green's function, and we have identified we solved the Green's function and obtained an expression of Green's function. Next, what we did, we evaluated the adjoint operator, that was the step number 3. We evaluated the adjoint operator and found out that adjoint operator is not same as the original operator. The adjoint operator turned out to be in this case minus del del t del square del x square. Next, what we did, we obtained expression of adjoint Green's function from expression of Green's function by changing the subscript. And using the relationship between G and G star, and after that what we did, we connected original PDE with adjoint Green's function operator. And what we did after that, we simplified. So, we have taken the inner product of our original equation with the G star and the inner product of governing equation of G star with U, and then we subtracted, and that way these two are connected. So, finally, I am just writing the final. So, we simplified the in between steps, and the final expression we obtained is that on the left hand side you had minus h, if h is constant it will be 0 to 1 G star at t is equal to 0 dx plus 0 to t 1 q is constant del G star del x evaluated at x is equal to 1 dt minus p integral 0 to t 1 del G star del x at x is equal to 0 dt is equal to right hand side 0 to t 1 0 to 1 f G star dx dt minus u of x 1 and t 1. Now, what we did, we obtained up to this expression. Then what we should do, we take the this one on the other side and see what we get. So, u x 1 t 1 is nothing but double integral f G star dx dt 1 over x 1 over t plus p 0 to t 1 del g star del x evaluated at x equal to 0 dt plus q 0 to t 1 del g star del x evaluated at x is equal to 1 dt. Okay, this will be minus when you change the sign, and this will be plus h 0 to 1 g star at t is equal to 0 times dx. So, if you see on the right hand side, there are 4 terms corresponding to 4 non-homogeneities in the governing equation. So, these cover these volume integral, since it is a 2-dimensional problem, double integral is nothing but a volume integral. This volume integral corresponds to the non-homogeneous term in the governing equation. This surface integral over t corresponds to the initial non-homogeneous initial condition in the governing equation, in initial condition in the original problem, and this non-homogeneous term corresponds to the non-homogeneity occurring at the boundary condition of the original problem, and this non-homogeneous term will be corresponding to the non-homogeneity present in the initial condition of the original problem, and this non-homogeneous term will be is corresponding to the non-homogeneous term present in the boundary condition of the original problem at the boundary x is equal to 0. Now, so there will be 4 integrals I1, I2, I3 and I4. So, what I will do? I will just evaluate one of these integrals one after another to demonstrate this problem. So, for that, for demonstration, what you need? You require the expression of g star, and we have already developed and obtained the expression of g star, that is nothing but root over 2 summation n is equal to 1 to infinity sin n pi x sin n pi x 1 e to the power minus n square pi square t 1 minus t. Now, in order to evaluate these 3 integrals, what we need to evaluate? We need to evaluate g star at t is equal to 0, that is number 1. Second, we have to evaluate del g star del x at x is equal to 0. We have to evaluate del g star del x at x is equal to 1. So, let us do that. So, g star evaluated at t is equal to 0 is nothing but root over 2 summation sin n pi x sin n pi x 1 e to the power minus n square pi square t 1 del g star del x will be nothing but. So, let us first differentiate this one. N is equal to 1 to infinity n pi cosine n pi x sin n pi x 1 e to the power minus n square pi square t 1 minus t. So, that is del g star del x. So, del g star del x evaluated at x is equal to 0 is root over 2 n is equal to 1 to infinity n pi sin n pi x 1 e to the power minus n square pi square t 1 minus t, and del g star del x evaluated at x is equal to 1 is equal to root over 2 summation n is equal to 1 to infinity n pi cosine n pi sin n pi x 1 e to the power minus n square pi square t 1 minus t. So, we evaluate these 4 terms, and then we will be in a position to evaluate all these integrals one after another. Let us talk about the volume integral is I1 and consider, assume f is constant. So, f is brought out of the integral sign. So, integral from 0 to x is equal to 0 to 1, from t equal to 0 to t1. So, this will be summation root over 2 sin n pi x sin n pi x1 e to the power minus n square pi square t1 e to the power n square pi square t dt dx. So, this will be nothing but f x is equal to 0 to 1. So, we do the integration with respect to t first, then we will do the integration with respect to x. So, or we can do it simultaneously. So, since this is a product term, we can do the integration over t varying part. Whenever we will be doing the integration of t and x, the terms containing x1 and t1, they will be treated as constant. So, I am just writing directly, probably omitting one step in between. 0 n equal to 1 to infinity root over 2 sin n pi x1 e to the power minus n square pi square t1, and then the integration of sin n pi x dx, integration of e to the power n square pi square t dt. So, this will be minus cosine n pi x divided by n pi. So, this from 0 to 1 and e to the power n square pi square t divided by n square pi square. So, this will be 0 to t 1. So, this will be f root over 2 f summation n is equal to 1 to infinity 1 minus cosine n pi divided by n pi to the power 3 sin n pi x 1 1 minus e to the power minus n square pi square t 1. So, that is I 1. Now, let us evaluate I 2, I 3 and I 4. I 2 I am just evaluating in detail. I 2 will be h 0 to 1 g star at t is equal to 0 times dx. So, h and g star at t is equal to 0, we just put 0 to 1 root over 2 summation n is equal to 1 to infinity sin n pi x 1 e to the power minus n square pi square t 1 0 integration is there. So, it will be sin n pi x dx. So, this will be nothing but root over 2 h n is equal to 1 to infinity sin n pi x 1 e to the power minus n square pi square t 1 integral 0 to 1 sin n pi x dx root over 2 h n is equal to 1 to infinity sin n pi x 1 e to the power minus n square pi square t 1 1 minus cosine n pi divided by n pi. So, second term becomes root over 2 h n is equal to 1 to infinity 1 minus cosine n pi divided by n pi sin n pi x 1 e to the power minus n square pi square t 1. Okay. So, we evaluate the third integral. So, this goes the second integral, then we evaluate the third integral. Third integral goes like this: I 3 is equal to q summation root over 2 n pi cosine n pi sin n pi x 1 0 to t 1 e to the power minus n square pi square t 1 e to the power n square pi square t dt. This term T1 containing term will be treated as constant. So, this will be root over 2 q summation n is equal to 1 to infinity cosine n pi over n pi. So, there will be n square pi square there. So, 1 n pi will be cancelled out, sin n pi x 1 1 minus e to the power minus n square pi square t 1. Then I evaluate the term number 4 I 4, and I 4 I am just writing the complete solution directly, omitting a step in between. N is equal to 1 to infinity 1 over n pi sin n pi x 1 1 minus e to the power minus n square pi square t 1. So, if you see that each of the term I 1 to I 4 they will be they are containing x 1 and t 1. So, we will be getting x 1 t 1 is equal to I 1 plus I 2 plus I 3 plus I 4, each of these terms containing their function of x 1 and t 1. Then we change the running variable x 1 t 1 into x and t on both the sides, and we will be getting the complete solution of u x t at I 1 plus I 2 plus I 3 plus I 4, which are functions of x and t, and you will be getting an analytical solution for this particular problem using Green's function method. And this method demonstrates that how one will be getting an analytical solution using separation using Green's function method and combining the separation of variable problem with the Green's function method to obtain the complete solution. Now, there are we finish the parabolic partial differential equation non-homogeneous, which has to be solved using Green's function method, and I demonstrated how a parabolic partial differential equation can be obtained by using partial eigenfunction expansion method. Now, next what I will be taking up, I will be taking up the parabolic partial differential equation, but with the various other boundary conditions, and see how the Green's functions will be looked like and how the solution will be composed of the eigenvalues and eigenfunctions. Now, let us look into this problem. I will not be completely solving this problem because the earlier problem is completely solved. So, if anyone is interested, you can solve the problem these problems completely. I will just proceed up to some crucial points and then hand it over to you. So, this is the governing equation, parabolic partial differential equation we are talking about. At t is equal to 0, u is equal to h, at x is equal to 0, we have del u del x is equal to let us say q, and at x is equal to 1, we have u is equal to 0, u is equal to let us say p. Suppose these are the solution, this is the governing equation. There are 3 sources of non-homogeneity, all the initial and boundary conditions are non-homogeneous, and the governing equation containing this non-homogeneity f as a function of x and time. Now, if we so what will be the construction of causal Green's function? The the governing equation of causal Green's function looks something like this. It will be del g del t minus del square g del x square is equal to delta x minus x naught delta t minus t naught. So, that is the construction of causal Green's function. Now, we have replaced the non-homogeneous term in the governing equation by a Dirac delta function of 2 dimension, and then we substitute, and then we write down the initial and boundary conditions. At t is equal to 0, g is equal to 0, at x is equal to 0 and x is equal to 0, we should have del g del x is equal to 0, at x is equal to 1, we have g is equal to 0. Now, if you look, the initial condition was u equal to h. So, we write g is equal to 0. We homogenize the initial condition. then the boundary condition was at x is equal to 0, del u del x was equal to q. So, del g del x will be equal to 0 there. We just wrote the same form of the boundary condition, only the non-homogeneous term is forced to be homogeneous, and at x is equal to 1 the derivation boundary condition prevailed, u is equal to p. So, therefore, this will be g is equal to 0. Now, if you look into the partial eigenfunction method, the corresponding eigenvalue problem will be d square phi n dx square plus lambda n square phi is equal to 0, and this for this partial this eigenvalue problem, the mother problem is the Green's function. So, it must satisfy the boundary conditions of the Green's function, and both the boundaries were homogeneous. So, we write the boundary condition on the this eigenfunction. So, at x is equal to 0, we had del g del x is equal to 0. So, therefore, this will be d phi n dx is equal to 0, and at x is equal to 1, we had g is equal to 0. Therefore, phi n should be equal to 0. Now, we have already seen this problem. This problem is a standard eigenvalue problem. We have solved this problem, and we have found out the eigenvalues will be 2n minus 1 pi by 2, and eigen functions will be nothing but some constant c cosine lambda n x. And if you make the eigen function orthonormal, this becomes 1 and c n becomes root 2. So, the orthonormal eigen function becomes root over 2 cosine lambda n x. So, therefore, if you remember, if you compare to the earlier problem, in the earlier problem we had derivation boundary condition. So, therefore, in this problem we have a Neumann boundary condition, and if you the eigen values will be 2n minus 1 pi by 2 instead of n pi, and eigen function will be root over 2 cosine 2n minus 1 pi by 2 x or cosine lambda n x instead of sin n pi x or sin lambda n x. Now, if you look into the corresponding Green's function solution, the expression of Green's function becomes x t x naught t naught will be nothing but h t minus it will be is equal to 0 for t less than t naught, and this will be is equal to root over 2 summation n is equal to 1 to infinity cosine lambda n x naught cosine lambda n x exponential minus lambda n square t minus t naught for t greater than t naught. So, therefore, this is the Green's function solution will be obtained, and if you look into the problem that in the earlier problem we had the sine functions as the eigen functions, and in this case we will be having the cosine functions as the eigen functions, and the eigen values will be 2n minus 1 pi by 2 instead of n pi. Now, if you again in this problem the operator remains is not a self adjoint operator, because L star remains the same del del minus del del t minus del square del x square. So, again we will be constructing the causal Green's function, the adjoint Green's function. The governing equation of adjoint Green's function will be nothing but del g star del t minus del g star del t minus del square g star del x square is equal to delta x minus x 1 delta t minus t 1. This will be nothing but this is in compact form. It can be written as L star g star is equal to delta x minus x 1 delta t minus t 1. So, we now connect this equation with the original problem del u del t is equal to this is plus, there is no minus, del u del t is equal to del square minus del square u del x square is equal to f, which may be a constant, which may be a function of x and t, a prescribed function. So, then we connect u and this equation and this equation by taking the inner product of this equation with u, taking the inner product of this equation with g star and subtract, and we will be getting the corresponding solution. And I am not going to solve this problem for you. You can in the last problem we have solved this problem completely. So, you will be getting an expression of x 1 t 1, and there will be again 4 terms on the right hand side. First term will be corresponding to a volume integral, 1 is over x and t dx dt. You will be getting a so this term corresponds to the non-homogeneity term in the governing equation, then another term over non-homogeneity on the surface. So, it will be the non-homogeneous term in the governing equation at x is equal to 0, then one surface term will be a non-homogeneous term at, because of the non-homogeneity at x is equal to 1, then one more equation you will be getting over space, that is the non-homogeneous term present in the boundary condition, in the initial condition. So, there will be 4 such terms will be appearing on the right hand side corresponding to the 4 non-homogeneities in the governing equation and the boundary conditions and initial condition. Please note, since the problem is a 2-dimensional problem, the volume integral is a double integral and the surface integrals will be basically the single integral or one integral. In case of a 3-dimensional problem, the volume integral would have been a triple integral, the surface integrals would have been a double integral. For a single variable problem, 1-dimensional problem like in ordinary differential equation, we have already seen earlier that the volume integral will be a single integral and the surface conditions would be, that is, it will be the algebraic equation corresponding to the bilinear concomitant term type of thing. So, we have got the complete solution for this problem as well. Please complete this problem, that will give you a fair practice of solving such problems. Then I will be considering one more problem, which will be a Robin mixed boundary condition, and let us see how things look like. So, in this case del u del t is equal to del square u del x square plus f of x t in general, that is the governing equation at t is equal to 0, u is equal to let us say h, at x is equal to 0 we had del u del x, okay, at x equal to 0 we have a u is equal to p, at x is equal to 1 we had a Robin mixed boundary condition, that is del u del x plus beta u is equal to q, let us say. So, there are again 4 sources of non-homogeneity, one in the governing equation, another is the initial condition, rest 2 are on the boundary conditions present in the boundary at x is equal to 0 and x is equal to 1. Now, please note that again the corresponding, let us look into the form of governing equation of causal Green's function. Of causal Green's function, this will be del g del t is equal to del square g del x square plus delta x minus x naught delta t minus t naught. So, at t is equal to 0 we had u equal to h. So, therefore, g is equal to 0, at x is equal to 0 we had u is equal to p. So, therefore, g is equal to 0, at x is equal to 1 we had del u del x plus beta u is equal to q. So, this is del g del x plus beta g is equal to 0. So, if you just see, we have kept intact the forms of the boundary conditions, but made them homogeneous. So, that is the only thing, and the non-homogeneous term in the governing equation is replaced by the Dirac delta term. Now, if we see the corresponding eigenvalue problem by partial eigenfunction expansion method. The corresponding eigenvalue problem will be del d square phi n dx square is equal to plus lambda n square phi n is equal to 0. So, boundary conditions of this problem must be satisfying the boundary condition of the Green's function. At x is equal to 0, your phi n was equal to 0, at x is equal to 1, d phi n dx plus beta phi n must be equal to 0. So, we have already solved this problem. This is a standard eigenvalue problem with homogeneous boundary conditions. We have already solved this problem earlier. If you remember, the eigenfunctions are sine functions in this case as well, sine lambda n x, and eigenvalues are lambda n's are basically roots of the transcendental equation. That is lambda n tan lambda n plus beta is equal to 0. So, this was the form of the transcendental equation and the eigenvalues are the roots of this equation. So, therefore, in this case, if you look into the expression of Green's function, the expression of Green's functions becomes x t x 0 t 0 is nothing but h Heaviside function t minus t 0 summation root over 2 sine lambda n x naught sine lambda n x exponential minus lambda n square t minus t naught. Okay. So, again we can make the eigenfunction orthonormal to some constant. So, eigenfunction orthonormal means norm of phi n square is equal to 1, that will give C 1 is equal to some value, but in this case let us look what C 1 will be obtained. So, it may not be root over 2. Okay, we will be solving this problem. Let us say we make norm of phi n square is equal to 1. So, this becomes C 1 square integral sine square lambda n x dx from 0 to 1 is equal to 1. So, this will be C 1 square by 2 sine square lambda n x. So, it will be 1 minus cosine 2 lambda n x dx equal to 1. So, this will be from 0 to 1, we carry out the integral. So, this becomes 2 C 1 square is equal to 1 minus cosine 2 lambda n x divided by integral cosine 2 lambda n x. So, this becomes sine 2 lambda n x divided by 2 lambda n from 0 to 1. So, it will be 1 minus 1 over 2 lambda n and sine 2 lambda n, because the if you put the lower limit this becomes 0. So, sin 0 is 0. So, we put it like this form 1 by 2 lambda n sin 2 lambda n, we write it in tan 2 lambda n. So, this becomes 2 tan lambda n divided by 1 plus tan square lambda n, and we know tan lambda n is nothing but minus beta by lambda n. We have already proved that these two will be cancelled out. So, 1 minus 1 over lambda n, it will be minus minus plus beta lambda n square divided by 1 plus beta square divided by lambda n square. So, this becomes 1 plus beta divided by lambda n square plus beta square. So, we get an expression of C 1 from here. So, 2 by C 1 will be nothing but beta plus lambda n square plus beta square divided by lambda n square plus beta square. So, therefore, this becomes C 1 equal to 2 lambda n square plus beta square divided by lambda n square plus beta plus beta square. So, that will be the C. So, therefore, the eigenfunction becomes quite straightforward. The eigenfunctions, okay. So, this becomes since it was C1 square by 2. So, this will be 2 by C1 square. So, there is a square there. So, C1 square. So, C1 square will be there. So, you will be getting C1 as root over 2 lambda n square plus beta square under root divided by lambda n square plus beta square. So, that is the constant. So, eigenfunction becomes root over 2 lambda n square plus beta square divided by lambda n square plus b plus beta square sin n pi x in this particular problem. So, these are the eigenvalues. So, one can get the expression of eigenfunction. So, these are the eigenfunctions. So, one can get the expression of Green's function in this particular case. So, Green's function becomes g x t x 0 t 0 is nothing but h t minus t naught. Then this constant will be appearing root over 2 n is equal to 1 to infinity. Then this becomes lambda n square plus beta square divided by lambda n square plus b plus beta square root over, and then sin n pi x naught sin n pi x exponential minus lambda n square t minus t naught. So, that is the expression of Green's function. Once we get the expression of Green's function, one can get the expression of adjoint Green's function by using the formula g x 0 t 0 x 1 t 1 is equal to g star x 0 t 0 x 1 t 1 is nothing but g x 1 t 1 x 0 t 0, and by changing the subscript we can get the expression of g star, the analytical expression we can obtain as we have demonstrated earlier. So, once we do that, then what we do, we formulate the again the operator remains the same, because it becomes del del t minus del square del x square. So, we construct the governing equation of g star, that will be minus del g star del t minus del square g star del x square is equal to delta x minus x 1 delta t minus t 1, and we know the boundary conditions on g star the way we have done it earlier. At t greater than t 1 g star is equal to 0, t greater than t 1 g star is equal to 0, at x is equal to 0 your g star is equal to 0, at x is equal to 1 del g star del x plus beta g star is equal to 0. So, this is the governing equation and the boundary conditions on adjoint Green's function. Then what we do, we connect the actual problem with the with this adjoint Green's function. The actual problem was del u del t minus del square u del x square is equal to f of x and t. It may be constant, it may be function of x, it may be function of time, may be function of both. Now, we connect, we take the inner product of this equation with respect to u, we take the inner product of this equation with respect to g star, and we subtract, and we will be getting the solution of u x t x 1 t 1. So, there will be 4 terms again on the right hand side. These 4 terms will be corresponding to the volume integral or the non-homogeneous term in the governing equation. There will be 1 term over t. So, that will be from 0 to t 1 and another term over t. So, 0 to T 1 dt. These two terms corresponds to two non-homogeneous term present in the boundary condition at x equal to 0 and boundary condition at x is equal to 1, and then we will be having one term over x, that will be something multiplied by dx, and this term corresponds to the initial condition, non-homogeneous initial condition of the original problem. So, that is how we have seen that how the parabolic partial differential equation will be tackled for different boundary conditions and initial conditions, and we have seen that we have looked into all the three boundaries, that is the Dirichlet boundary condition, Neumann boundary condition and Robin mixed boundary condition. Only one thing will change, the eigenvalues, eigenfunctions and eigenvalues will change, and the corresponding expression of G star corresponding expression of Green's function will be different, because all these three problems will be having three different eigenvalues and three different eigenfunctions. So, once we do that, then we will be able to construct the causal Green's function by the expression of causal Green's the adjoint Green's function by changing the subscript simply. Then we will formulate the adjoint Green's function and connect it with the original problem, and we will be getting the complete solution in these three different for the three different boundary conditions of the parabolic partial differential equation. So, that completes the solution of non-homogeneous parabolic partial differential equation. Next, we will be looking into a more popular another popular partial differential equations, non-homogeneous, that is the elliptical partial differential equation with a non-homogeneity in the governing equation as well as in the boundary conditions. Now, the these types of problems, the elliptic problems, becomes very common and rampant for the steady state chemical engineering processes, which is multidimensional. So, for multidimensional steady state chemical engineering processes, with a source or sink term is represented by non-homogeneous elliptic partial differential equation. So, I will just take up an example. Of non-homogeneous elliptic PDE using Green's function method. Okay. Now, again we will take up the problem in rectangular coordinate. We can convert all this problem in cylindrical polar coordinate or spherical polar coordinate by selecting the appropriate operator. So, I am just demonstrating these problems in case of in Cartesian coordinates or in rectangular coordinate, because the solutions, the eigenfunctions etc., becomes very simplified. Now, let us look into the elliptical problem. Del square u del x square plus del square u del y square is equal to some function of x and y. It may be a constant, it may be a sole function of x, it may be a sole function of y, it may be a function of x and y both, but we are talking about a two dimensional problem, but in a general problem, for general case, the Laplacian is represented by del square del x square plus del square del y square plus del square del z square. So, at x equal to 0, there are four boundaries. At x equal to 0, u is equal to u 0 1, at x is equal to 1, we had u is equal to u 0 2, at x at y is equal to 0 we had u is equal to u 0 3 and at y is equal to 1 you have u is equal to u 0 4. So, there are 4 sources of non-homogeneity and we have considered differential boundary conditions on all these 4 boundaries. So, differential boundary condition on all the 4 boundaries and these 4 are non-homogeneities and one boundary the initial condition was non-homogeneous. Now, if you examine this problem, unlike the earlier problem, the parabolic problem, if you looked into the parabolic problem was having the operator was del u del t minus del square u del x square and the corresponding eigenvalue problem will be grad square d square phi n dx square minus plus lambda n square phi n. How that the eigenvalue problem will be cropping up? The eigenvalue problem will be cropping up by the formulation of construction of causal Green's function. So, if you remember in the earlier I am just talking about the earlier problem. In the earlier problem the causal Green's function was formulated by forcing all non-homogeneities to be 0 except the non-homogeneity in the governing equation is replaced by a Dirac delta function. Now, since the boundary conditions are homogeneous in the earlier problem, we formulated the corresponding eigenvalue problem in the x directions simply because the mother problem, which was the Green's function problem, was having homogeneous boundary conditions. So, in this case, if we look into the corresponding causal Green's function, so causal Green's function will be del square g del x square plus del square g del y square is equal to delta x minus x naught delta y minus y naught. So, what we did, we replaced the non-homogeneity in the governing equation by Dirac delta function located at x naught and y naught. Then we make all the boundary conditions to be homogeneous at x is equal to 0, g is equal to 0, at x is equal to 0, at x is equal to 1, g is equal to 0, at y is equal to 0, g is equal to 0, at y is equal to 1, g is equal to 0. So, if you look into the construction of causal Green's function, we replaced the non-homogeneous term in the governing equation by a unit by a Dirac delta function located at x naught and y naught, and all the non-homogeneous boundary conditions are forced to be homogeneous. Now, if you look into the boundary conditions, that both the boundary conditions in x directions are homogeneous, both the boundary conditions in y direction are homogeneous. So, therefore, we can formulate the standard eigenvalue problem both in x direction and y direction independently. So, we can and there are the dimension is a 2-dimensional problem. The independent variables are x and y. In both x direction, we have an independent eigenvalue problem. In the y direction as well, we have an independent eigenvalue problem. So, this problem can be broken down into the Green's function can be expressed as a function of the eigenfunctions in the x direction as well as eigenfunction in the. So, we are looking into the causal Green's function of elliptical partial differential equation, and we have seen how to formulate the Green's function in such case. And if you remember that even the original problem, the boundary conditions are not homogeneous, we have to force the boundary conditions to be homogeneous in case of formulation of Green's function. So, the non-homogeneity in the governing equation is replaced by the Dirac delta function in the unit step function in the governing equation of Green's function, but all the boundary conditions are to be forced to be homogeneous. In other words, we are trying to find out what is the effect of the non-homogeneous term source term in the governing equation, keeping all the other non-homogeneities to be vanished, so that we can ideally identify what is the non-homogeneity in the governing equation in the of the original problem will reflect in the final solution. Then we will hook up this problem with the actual problem governing equation of u, and then coupling with that we will be getting the complete solution. So, in this class we have looked into the solution of complete solution of parabolic partial differential equation non-homogeneous, and how to use how to solve that equation by using Green's function method. So, in the next class I will take up the complete solution of elliptical partial differential equations, which will be quite common in steady state chemical engineering processes. So, in case of partial differential equation, or in case of the causal Green's function formulation in elliptical problem, you must have understood that all the boundary conditions are homogeneous. That means, we can have a standard eigenvalue problem in the x direction, and we can have a standard eigenvalue problem in the y direction as well. Therefore, we will be utilizing the full eigenfunction expansion method in order to obtain the Green's solution of Green's function. Then we will be hooking it up with the actual problem in order to get the complete solution. So, I will stop here in this class. I will take up this problem in the next class and completely solve the Green's function solution of for the elliptical problem, and then I will again just couple the solution of Green's function with the original problem and see how the complete solution evolves out of it. Thank you very much.